All right, hi everyone. In this example, we are going to consider a case where the area is changing. It is question 227. Let's read the question first. Question 227. In the accompanying figure, the rod slides along the conducting rail at a constant velocity v. Find the formula for the EMF and the direction of the induced current. So basically what we have here is two conducting rail. There's a resistance connecting the tip of both rail, and there's also a conducting rod. Now, this forms a closed loop, and this conducting rod is moving to the right, which means the area of the closed loop will be increasing over time. Also note, there's a magnetic field, and it is pointing into the board. So as we increase the area, the number of magnetic field lines going through the board will increase. That's an important detail, and it will be useful when we have to determine the direction of the current. So the first thing we need to do is get an expression for the change in the area. If we were to calculate the area after a certain amount of time, after displacement delta x, we could find the area by equating it to delta x multiplied by the length. Now the length here will be the distance between the rod, and it makes sense. If we move the conducting rod a little bit, well, we multiply the displacement by the distance between the two rails, and we got our area. All right, now we want to find the change in area with respect to time. So we take that term and we divide by delta t, so the time elapsed. This only works, by the way, because the velocity is constant. Now, there are many interesting questions we could ask if the velocity was not constant, in other words, if the acceleration was not zero, but they are more complex and I don't want to cover them in this course, all right? So we are going to stick with this format of question, and in this case, since the velocity is constant, we can simply do the derivatives of the area will be equal, derivatives of the area with respect to time, it will be equal to the change in displacement divided by the change in time multiplied by L. Well, these two terms over here combined together is equal to the velocity. All right. We are now equipped to find the EMF. So EMF is equal to the change in flux is equal to, basically, there's a missing term over here, is equal to the derivative with respect to time of that term, magnitude of the magnetic field multiplied by the area multiplied by the cosine of the angle. Again, the area vector and the magnetic field, their angle is 0, so cosine 0 will be equal to 1. Magnetic field is a constant in this case, and multiplied by dA divided by dt. Well, in this case, we already found out that it's dL. So we get an easy formula. The EMF is equal to BVL, so the magnetic field multiplied by the velocity multiplied by the length. The length here is the distance between the two rails. That's important. Often the length can mean different things. In this case, it is the distance between the two rails. All right, so we know the magnitude. This is the formula. We want to figure out in which direction the current will be pointing. So, as I said previously, we have the rod moving to the right, and the number of field lines going into the board will increase. If the number of field lines going into the board increase, that means that the closed loop will react by inducing an opposite magnetic field. So it will create a magnetic field pointing in the opposite direction. So we point our thumb toward the induced magnetic field, and the curl of our finger indicating which direction the current will be pointing. In this case, it will be counterclockwise, all right? So it will be CCW, so counterclockwise, all right? So that's it for question 227. We're going to be solving another question that is quite interesting involving that very principle. And after that, we're going to tackle generator, and we will be almost done with this chapter. And yeah, that's it. So let's switch to the next example.